and record what I do, or the important bits of what I do, pausing it now and again when you guys are working on something, put the videos on YouTube, and I'll link them into Moodle. I'm still looking at how best to lay them out so they look nice and you can find what you want easy, but I'm working on that. Right. I thought we'd first have a look at the module description and just see what the learning outcomes are for this module. So the title is Electrical Systems and Fault Finding. Level 4's got a credit value of 15. Learning outcomes. Investigate the constructional features and applications of electrical distribution systems, which is where we're going to start today. Examine the types and applications of electrical motors and generators. Analyze the types of lighting circuits available in industry by assessing their practical application, and explain the operating characteristics of electrical safety components. So on the next page, essential content for each of the learning outcomes. So that tells me what I have to teach for that learning outcome. Not all of that is assessed. Yeah. So they pick bits from that to put in the assessment. Yeah. And then, so these are the kind of things we'll cover. And it's up to me to interpret that and decide which things are most important, which things might be more of a background, just information thing. But obviously the key things are what you're going to be assessed on. Yeah. So I'm not going to dwell on that too much, but we will have a look at the assessments. Now, in a way, the 4 learning outcomes are quite disparate in that they have kind of 4 separate topics that don't necessarily correlate with each other too much. And that's laid out so you do 4 assignments. So you're familiar with how these are laid out, and they are on the assignment briefs, so you'll be familiar with that. You've got to do all the pass all of those, get all of those and that to get a merit for that assignment, and get all the passes and a merit and a distinction to get the distinction grade for that assignment. Yeah. And then you've got to get all the merits to get an overall merit, and all the distinctions to get an overall distinction, and so on. So you're all familiar with that. Now, initial thinking here was 4 separate assignments. Bearing in mind we got 15 weeks for teaching. You're talking about 3 and a bit weeks for the teaching of each assignment. What I would do there is issue assignment 1 probably next week, so you can start work on the bits that we've already covered, and then build on that over the 3 weeks teaching, and then maybe have another couple of weeks to finish that off and hand it in. Yeah. So we'd do that 4 times, and you'd have 4 assignments with 4 deadlines, and I'd have 4 lots of marking to do. An alternative to that I've started to think about today, and I just need to have a chat with Roy about it, I think, before he's off, is to join together 2 learning outcomes in each of 2 assignments. So overall the work won't be any less, but I can split the time up better, because I can still issue the first assignment early, and you can start work on the bits that you've done, but have much longer to do it. I can't promise you time to do assignment work in class. I don't know how much you got with Roy time in class to do assignments, but we haven't got a great deal of time, and you wouldn't have. I mean, if I compare this to the other course that I've been teaching, foundation degree, a module, admittedly 20 credits instead of 15, would be 200 hours work for a student, but only 50 of those as the in-class time. So 150 hours per module meant to be spent in your own time doing work. So, you know, that's something you've got to face. And I know what the feedback was when the external come in the other week, that there was a lot of work to do, and I'm aware of that, but there ain't a great deal I can do about that. That's how much work there is to do. That's how much you've got to do. So whilst there might be time to work on them sometime and get a little bit of kind of feedback as you go along, that can't be promised. All right, because particularly when we start out here, I don't know how long this is going to take and how much input I'm going to need to do each week. So we're going to have to suck it and see. All right, and you're probably going to have to do some work at home. All right, but what do you guys think? Who thinks 4 separate assignments would be better at this stage? Either have, what I was thinking, and that might end up 3, I can see a reason to put learning outcome 1 and 4 about safety devices together. And there is a tendency for me to see a link, partial link there. Yeah. I mean, I don't know the deadlines for them, so I'd have to check with Umal. But I mean, the best we could do is what I do on a foundation degree, is make sure that you haven't got 2 hand-ins in 1 week. I can't make sure that you haven't got 2 or 3 assignments over different modules to work on in a period of time, because that wouldn't be feasible. So I can't completely separate my assignments from Umal's in terms of work. But what we can do is look at the deadlines so that you don't get 2 deadlines in 1 week. And we always do that on the degree. So we make sure that although you might have 2 or 3 things to work on, the deadlines are separated. Yep. I mean, generally there aren't as many assessments on that, but there are examinations that you haven't got, so there's always pluses and minuses on everything. Right? Like I was saying, I can see a reason to perhaps join together learning outcomes 1 and 4, but these 2 middle ones, 2 about motors and generators and about lighting systems, don't really look as though they fit together, but I could put them in 1 assignment. Or I could do 3, and that might be, I have to think about it for a little while before making a final decision on that. But I'll have a chat with Roy and with my other colleague and see what he thinks. Yeah. Well, yeah, you're still going to have, you've got to pass the same criteria, so it will be, but I can better apportion the time for you to be able to do that, in my opinion. Well, if I choose to join 1 and 4 together, I'll teach 1 and 4, then I'll go 2 and 3. Yeah? All right? So you think less assignments is better? Yeah. 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 Well, I'll try. I'll have a word, and like I say, I need to talk to other people and make sure that's a good way to go. But I'll do my best. All right. So that's where we are. That's when you get the assignments, you'll have these, so you'll know what you've got to do, and you'll know, if you read them carefully, you'll know which bits are which. Yeah. We're not to identify which bits are merit and which bits are distinction, but I won't take too much brains to work out which bits are which. Yeah. All right, so that's the module, and that's what we're going to be doing over the next 15 weeks. Yeah, we've got this week and next week, and then we've got a half-term week. I'm sure you're all aware of that. Yeah, that's what it is. All right, so I guess some of you will be back to work for that week. Right, having done that, let's have a look at what we're really going to do. So, HNC, Operations Engineering, Unit 31, Electrical Systems and Fault Finding. I'm Mike Betts. That's my email address. I live where Roy lives currently, in room 408, if you want to try and find me. Alright. I only work Tuesday to Thursday. So after going home time Thursday, which is upper state tonight, you'll get out of office emails off me until the following Tuesday. Alright, so send me them by all means, but it's highly unlikely you'll get a reply over the weekend. Alright, but you will get replies if you email me when I come back on o'clock. I'm only part-time, so be it. I've got some handouts of this stuff for you. Just pause that because I haven't had time to prepare anything, or it's not appropriate. Alright, but where it is, and I've got something for you, I'll always do it. The other thing I do is I'll put the blank copy of this on Moodle, and I'll also at the end of the session PDF the file that I've scribbled all over on the board and put that on as well. Alright? So you'll tell the difference by the file that I've scribbled all over will have the date on it as well. So it'll have the date of the session. Right. So we're going to start off, we looked at the learning outcomes, so I won't dwell on them. I'm going to start off having a look at some basic electrical formulae, refresher. Now, if all of you have done some kind of basic electrical qualification, you'll have all covered what I'm talking about here. If you haven't, then you won't. Okay. What I want you to do on the first 1, 2, 3, 4 pages from there's something about Ohm's law. There's a little bit about power, and there's a little bit about series and parallel resistance calculations. But fairly basic electrical science stuff. I'm going to go 10 minutes for you together to work together, go through that, and find out how much you already know. Yeah, about that kind of thing. So 10 minutes, just work on those first few pages. Right, guys, let's take a look, shall we? See what you already know. So Ohm's law. Formula for Ohm's law. What are you? Oh, you got this triangle you like, is it? Like I said, that's the relationship between voltage, current and resistance, and a lot of students like this triangle thing where I, V and R are in that like that, and voltage is current times resistance, current is voltage divided by resistance, resistance is voltage divided by current. Okay, I like to see Ohm's law as being I is equal to the voltage divided by resistance, and I say that because current is usually the thing that happens because of the other two. So you control current, or the amount of current that flows is dependent upon the voltage that you apply and the resistance of the circuit. And what's quite important to remember and helps a lot with electrical learning in electricity is that you remember that current, if we increase voltage, keeping resistance the same, current's going to go up. If you decrease voltage, current's going to go down. So it's said that current is proportional to the voltage you apply. Put the voltage up, current goes up. Put the voltage down, current goes down. Whereas that's inversely proportional to resistance. If we increase resistance but keep voltage the same, we're going to reduce the current. If we decrease resistance, we're going to get more current. If you can remember that relationship, you'll always remember Ohm's law. Okay? Yes, there are 3 different formulas because we rearrange that to V is equal to I times R, okay, and R is equal to V divided by I. Okay, and I'm okay with you remembering it by the triangle if that's what you like. I don't tend to teach that at this level. I did for level 2, but that's fine. All right. So using Ohm's law to calculate the current flowing in a circuit of resistance 25 ohms when 230 volts is applied, that's I is equal to 230 divided by the 25. They push the buttons. What do you get? Sorry? 9.2 amperes. And as you'll come to learn with me, I am hot on saying what the units are, because the units are very important. Okay, if you don't put amps there, it doesn't mean anything. All right. The other thing I'm quite hot on is if people say they're looking at a circuit and they say there's 25 volts going through that resistor. Now they're in. Current goes through, voltage is applied across. And that's about knowing those basic principles of what the current is. That's a measure of how much electrical current's flowing. Voltage is like the pressure you apply in a hydraulic circuit. It's what forces the current through. Yeah. So I'm quite hot on using the terminology correctly. Yeah. And I wouldn't like you to say put the current up or put the amps up. I wouldn't like that. You should say I'm going to increase the current, because amps is the unit, current is the quantity that you're changing. Okay. So moving on to the next page, power, the fourth key electrical quantity. It's the rate at which electrical energy is used and is measured in watts. Okay, with 1 watt being 1 joule per second. 3 different formula in general for calculating power, depending on what values you know. How many of these formulae do you know? Josh, give me the first one. P equals I times V. Yeah? Current times voltage. Alright? Who's going to give me another different one? Yeah? P is equal to V squared divided by the resistance. Yeah? And the third one? Yeah? P equals I squared R. Same thing. Alright? So with those 3 different formulae for power, you can all, as long as you know 2 of the quantities V, I and R, you can always find the power being dissipated. Yeah? So it's worthwhile knowing all 3 of those formulae so that you can calculate. Now, if you know 2 quantities, you can usually calculate a third one and then do another calculation to get the power. There's one combination that won't allow you to do that. Okay, so it's worthwhile knowing these 3 formulae as well, because then you can always get the power if you know 2. Alright? And a standard fare, and at this level you'd be expected to remember them. Yeah? So if we want to calculate the power dissipated from a resistor of resistance 15 ohms, if 230 volts is applied, like I say, if you always remember this one, you could calculate the current and then multiply it by the voltage. But the easiest way is to use what you've been given. Power is equal to 230 squared divided by that resistance. So hopefully someone's done that calculation. 3, 5, 2, 6. So if I wanted 4 significant figures, I'd make that a 7. Yeah? Watts. Yep. That's to 2 significant figures, Josh. Yeah? Alright. So if depends when you do calculations, particularly where you're using measured values from circuits, you must bear in mind the resolution that you've measured it to. So if your meter will only measure to that number of digits, you can't then go and quote 4, 5, 6, 7 digits from your calculator in the answer, because you're quoting more resolution than you've actually done your measurements to. So you should bear in mind how many significant figures you've got in your data and only include no more than that in your answer. Yep. So it's a judgment call. Generally, I think with my degree students, I talk about them using 3 or 4 significant figures through calculations. Generally, if you're carrying calculations through and you want 3 significant figures at the end, probably take 5 through each individual calculation and then round right at the finish. Yeah. So calculate the power of a simple motor with a winding resistance of 2.5 ohms if it's found that the motor draws a steady current of 1.2 amps. So here we're looking at P is equal to I squared R. It's the most convenient formula, because they're the 2 things we've been given, which is 1.2 squared times 2.5 ohms equals 3.6. Yeah. Okay, so nothing too difficult there so far. Oh. Okay, then what we may well come across at points in this module is resistors in combination, in series and parallel. So when we connect 2 resistors together end on end like that, we're said to be connecting them in series. Yeah. How do we calculate the total equivalent resistance of these 2 resistors if R1 equals 25 ohms and R2 equals 15 ohms? What do we do? Yeah. RT, for series, RT, R total, is equal to R1 plus R2. And we can go on and say if there's a third for any number, Rn of resistors. So just add them all up. But they must all be in one long series. If you think about it, current trying to go in there has got to get over the resistance of that resistor, and then when it gets out the other side of that one, that's got the resistance of this one. So overall, the resistance must be greater than any one of them. And in fact, it is both of them added together. Yeah. So in this case, we've got RT equal to 25 plus 15 equals 40 ohms. Yep. And that's true for any number of resistors. All happy with that? Yeah. Now, parallel resistance. This is where we have 2 or more resistors connected across each other. Yeah. So like they are there. For 2 resistors only, we can use this formula that's called the product over sum formula. Now, mathematical terms, product means multiply, so the product is multiply the 2 together, and that's product, and then sum. There's a quick way to do resistance. Yep. So in this case, RP would be R1 5 times R2 8 divided by 5 plus 8. 40 over 30 Everyone got it? 3.08 ohms. One thing to note of that is that the total for any parallel combination will always be smaller than the smallest resistor in that combination. So the smallest here is 5 ohms, and the total is less than that. Always will be. It's a useful thing to have up here. Bit of a check. If you push the button on your calculator, that total comes out higher for the lowest one, you've gone wrong somewhere. Yeah. If you think again about current, because that's got going in there, because that's got 2 different directions to go here before coming back that way, the overall resistance to current flow must be less than it would be if you only had one path. Yeah. And this total here is, what we're saying is we could take those resistors out of that circuit and put one in of 3.08 ohms, and we'd have the same circuit electrically and we'd have the same current flow. Yeah. So that's what we mean when we say the equivalent resistance. Right. How do we calculate the total if a third resistor of 10 ohms is also connected in parallel? So if we got more than 2. Yep, 1 over RT is equal to and that can go on for as long as you like. Yeah. Now, whilst I wouldn't want to cause confusion, yeah, what I find is sometimes students forget that this is 1 over RT. 1 over a number on your calculator is like a button that says x to the minus 1. That's what that means. The reciprocal of. All that button does is turn a fraction up the wrong way. If you do 10 in your calculator, press the x to the minus 1 button, what do you get? Yeah. Now press it again. Same button, x to the minus 1. 10. Yeah. Let's go on to a tenth and then turn it back up the other way. That's what that button. Another way of writing this formula is to say RT is equal to R1 to the minus 1 plus R2 to the minus 1 plus R3 to the minus 1 plus Rn to the minus 1. Close the brackets, all of it to the minus 1. So you're taking a reciprocal of everything in those brackets. But with the modern calculator, certainly the Casio, that's probably the quickest and easiest way to do it. Yeah. So you use whatever method you like, but if you use this one, when you press equals at the end of doing that bit, you must do x to the minus 1 on the answer to get the proper actual answer, because that says 1 over RT is equal to it. Yeah. So in the case of the example we've got, we can say RT is equal to 5 to the minus 1 plus 8 to the minus 1 plus 10 to the minus 1 all to the minus 1. And what do we know about the final answer for sure? It's going to be less than 5 because that's the smallest one. So do that on your calculator, please. And is that what you would expect? Or would you expect it to be even less when you add a third current? Yes, you would. Got now another route to go. Yeah. Now you can use that formula for 2 resistors if you want to. Put a plot up to on. It's probably the quickest way to do just do. Yep. Alright. We might meet circuits later on where we've got a resistor in series and two in parallel, like so, combination. Alright. Where you would deal with that is you'd calculate the total of those two in parallel and then add that one on afterwards. So you're kind of turning it into an all series circuit by getting the equivalent of these two and then adding that one on afterwards. Alright. The other type of combination is where you got this. Two in series in parallel with a third, and in that case you add those two together first and then parallel up the result with the third one. Alright? We'll have a go at that and I'll work through it if need be when we find out what calculations we need to do later on. Alright? So you're all happy with those basic calculations? Ohm's law, three different formulas for power, and the methods for calculating series and parallel equivalents. Yeah? Right, what I'm going to go on to now is distribution of electricity. So, the way that electricity is distributed in the country is that there are lots of different power stations situated, most of them near the sea, so they've got abundance of cooling water for their systems. But they're all connected together in a way that they're connected to a 400 volt kilovolt or a 275 kilovolt supergrid or national grid and linked together in a loop. And presume you may or may not already be familiar with that. Yeah, so we generate at around 22 kilovolts. Not all, I don't believe all stations do the same voltage, but they all feed onto the same grid. Yeah. So we get, they call that transmission at that voltage. So that's getting the electricity from the power stations into key areas. Yeah. And then it's the voltage is lowered to a range of different voltages depending on how big the area is and what consumers you got in that area. So you might have, so it's lowered down to 132 kilovolts, and if you have really large heavy industrial, I'd say, I know for sure, might take their electricity as a customer at 132 kV and have their own networks that reduces it to the voltages that they need. Alright. Then you might have 132 down to 33 kV, which would feed light industrial, medium-sized factories, and also local areas like a small town like Beccles will have a 33 kV substation. Then they have a distribution network at 11,000 volts that goes around various smaller substations to feed various states. I think is the best way to describe that. Yeah, and at those substations they then transform down to the 230/400 nominal voltages that we're used to if you have anything to do with electricity at work and or at home. Yeah. So those voltages quoted are what's called nominal voltages. So we all know as 230 volts at the circuits on the wall. Yeah. So stated voltage, not the peak. Alright, so when we talk a bit more some point about the sine wave, that voltage actually peaks at something like 330 volts. Yeah. And that's something that you need to be in mind if you're working with capacitors, that you need a capacitor that will take at least 330 volts because that's what the peak of that waveform is. The 230 is what's called RMS. Has anybody not heard of RMS? It stands for root mean square, and it's the equivalent DC value of that waveform. So it's the voltage that would give you the same power as 230 volts DC in the same circuit. And that's what your meter, your multimeter, measures as RMS. They also talk always about three phases. Everything but the 230 400 volt, there's a 3-wire system, and then at 230 400 volts, we go a 4-wire, so we can achieve the 230 and the 400 volt alternative voltages, and we'll do a little bit more about that later. Okay. You'll note that I've put a reference on there. Have Roy been through Harvard referencing system, will you? That's how you would write what's called the in-text citation for where I got the information from. And you'll see right at the end of the slides today, if you look, there's the full reference for where you can find that. Alright, so I've done that so that you can put that into your own work where you need to reference things. Yeah. So is there anybody who wasn't aware at all about how the grid works in this country? If you do research around that, what you need to do is be careful that you're finding information about the UK and not about the States or any other country. If you see the mention of 60 Hertz, for instance, you're not talking about the UK, because our frequency is 50 Hertz. Yeah? So we're going to kind of major on what's happening in our country here. So, what I want to do is have a little bit of a look at the kind of what's called one-line distribution diagrams and how those networks might be connected. So what we've got here is a typical what's called radial network, where we're coming off the national grid here at 400 kV, and this is a symbol for a transformer. More about it later, but these two symbols here are telling you that it's delta connected and delta, so both are 3-wire delta connections, primary and secondary. Alright, and that's telling you the voltages. So that's a transformer. This is a circuit breaker. And the thicker lines are called a bus. It's not something that drives down the road. It's like a big interconnection between a number of circuit components that's able to take a lot of current. So would normally be a big copper bar that all the circuit breakers can connect to. And these circuit breakers can stand this high, and they can be racked out and completely taken out of circuit. So they're huge great things. Has anybody ever seen the, I don't know, anyone got a 11 kV network at work and have seen the 11 kV circuit breakers? Yeah, yeah. No, you won't if you're not authorised to work in that area. You won't be. You won't be. Yeah. Where do you work, Dan? Yeah, you have a few there. Yeah. I taught a few people at Sizewell as well. Paul Dumble. Yeah. Yeah. Who else? Alan Winter. No. So, this feeds onto a 33 kV bus bar. It then has further transformers that transform down to 11 kV. You get an 11 kV bus, and then that feeds individual circuits and so on over there. If we look at this radial circuit, if we get a fault there, such that that circuit breaker trips, all these consumers lose supply. That's something to think about, that style of network. Yeah, and they get more complicated than that. Oh no, sorry, they won't. My fault. That's still supplied through that way. Now, you could get, in some cases, depending on how much each of these two sides is loaded, there might be a case where there's a interconnector between these two buses that's normally open, but they might be able to isolate the fault, close that and resupply some of these consumers that are lost supply, but only if that facility's there. Yeah? And quite often these will radiate off quite a lot, and a lot of people will lose supply if they get a fault high up the system. It just depends where it is. Alright? But you got to kind of get yourself familiar with these symbols, because part of the assessment here is that you're going to have to recognise some symbols and say what they are as one of the grade criteria. Alright? I'm going to give you a handout. Again, doing research, I found it quite difficult to find a solid standard that was UK. Found lots of different diagram types with close to this but with differences, and NEMA ones which are American system. But what I have found, the handout I've found to give you, has got a comparison of the key NEMA and IEC, which is what I've used here, IEC symbols. So I'm going to give you them now anyway. I'll also put this handout on Moodle as well. Star. Yes, star. Americans call it Y. They put up the other way and say it's a Y connection. I'll put it on the board in a minute, but you've got the triangle as the delta, and the other little symbol on the 400-230 is star. So that symbol there is star, that little one. Right? And like I say, our American friends put it this way up and call it Y. That's the same thing. So that's another indication that you're on a site that is talking about American stuff. They start talking about the Y connected transformer or the Y connected motor. Doesn't mean that's not relevant, doesn't mean you can't use it, but you should be aware that we're trying to major voltage wise on UK. Right? NEMA's the American system, yeah. I can't remember what the letters stand for, but I'm sure you can check it out, yeah. Right, if we look at, we're going to also look at one alternative style of network to connect. Right, lads. So, as opposed, I mean, I couldn't possibly find the time to go out and look at every single type of style of network that they might decide to connect. But one alternative, and I know this kind of thing quite well, because we were on this type of ring at Fibronile, an open 11 kV ring. So it had two supplies coming in, one, and we were on what they'd have as an open point. So sometimes they have it completely closed, sometimes they have a halfway point that's open. So effectively had 11 kV coming in from the left hand side and another 11 kV from the right, but the right one was isolated under normal conditions. But if we lost our power from left, we could phone up Millfield Control and ask them permission to switch that one off, because that's got a fault on it, and turn the other one on. So if we look at this system, again we're coming in from the 275 kV national grid down to 11 kV, and we got 33 kV. We've got a 33 kV bus there. All right, and I'll put a little note in the middle saying X denote means to isolate a faulty transformer from the bus. So what I'm saying there is there'd be some form of isolation between that bus and the transformer, so you could isolate it for a transformer replacement. But to keep this diagram reasonably simple, I've left that off. Alright, so in this case we're going down to from 33 to 11 there and there. Alright, unless this one remains open under normal conditions. So these consumers, or this 11 kV loop here, feeds closed through there, and feeds that customer, yeah, via that transformer. And this transformer through here, and there might be many more, I kept it reasonably simple, feeds to there, but that is open. Yep. Right, so we've got, because of that open point, we've got an alternative method of getting supply. If we get a fault on a couple here, for instance, what we do is open this to isolate that cable. And there's a plot, hang on, I want to go with my fault over the other side, sorry boys. Think about count. Fault there. Yeah. So that circuit breaker trips, and fibronol, or whoever that customer is, loses supply. Yep. So, what we can do is isolate here. Yep. So that we can switch that back on, or keep that on. This customer is supplied from that transformer. That's normal. They've lost supply via that route. But if we close this can now have supply from that route, so it can be reinstated. Yep. Now a further improvement on that type of system, because the danger is that you can still lose a lot of customers if something goes wrong at this point, is that you could have a second 33 kV feed-in. So again, further, you've got two alternative routes for the supply to come from. Yeah. Of course, all of that reconnecting the supply depends on both of these being able to take the load that you want to connect. So they might not be able to get everyone on, but they may be able to get a significant number dependent upon load. Yeah. So that type of system will give them more flexibility to get customers back on supply. Yeah. Does anyone here work at British Sugar? No. Well, I know at their sites at Cantley and at Bury Edmunds, they've got their own combined heat and power generating stations, because when they're on campaign, so important for them to have electricity. So they generate their own electricity, and when they're off campaign, they generate electricity and backfeed onto the national grid. So they become a supplier of electricity. And that's just one of the things British Sugar do to help make them almost energy neutral. They collect aggregates from there, from the soil that's on the sugar beet when it comes in, and grit and all sorts of things that they then sell off to help make them energy neutral. It's an interesting look if you're interested in that green kind of thing. And at Bury St Edmunds, they've got anaerobic digesters as well, so they're using the sugar beet waste to make methane to run their power station off. Have you? Oh, okay. Which site is that on? On, yeah. They didn't have one when I was there.